Yeah.
So with your permission, can we start, Professor Lakshmanan?
Yes, I'm ready.
Okay, great. So, so welcome back to the second post-lunch session, day 1, April 14th. And we're delighted to have Professor Muthusamy Lakshmanan, obviously a well-known nonlinear dynamicist. He's currently a professor of eminence at the Bharatidasan University. So I request Professor Lakshmanan to kindly give his talk. Thank you.
Yeah. Thank you very much, Professor Mitra, for your kind invitation in this wonderful meeting of Professor A.N. Mitra Memorial Meeting. To start with, I have to state that unlike many of the earlier speakers, I do not have a strong personal interaction with Professor Mitra as a student or a collaborator. But when I was a student in early 1970s, some of our heroes of theoretical physics in this country, starting from Professor P.M. Matthews, and then Professor A.N. Mitra, Professor S.N. Biswas, Professor Virendra Singh, Professor Mukunda, and Professor T. Pradhan were our heroes at that point of time. And so I had been following Professor Mitra's work from that time onwards. But it was during 1990s, early 1990s, I came into personal contact with Professor Mitra when we met in one of the INSA meetings, when he was kind enough to invite me to visit the Department of Physics, Delhi University. And during that visit, he was a great host. And I gave a talk on solitons and integrable systems related topics. And he was very attentive. And after that, he gave me a lot of encouragement and suggestions and so on. And then later on, he also invited me in 2006. I think a couple of earlier speakers had mentioned the book, India in the World of Physics, Then and Now. I think it was published in 2006. And Professor Mitra requested me to write an essay on nonlinear dynamics. So I wrote on nonlinear dynamics, an insider's perspective. And he was very kind enough to encourage me to write that article. And he ultimately agreed to publish that article. Okay. And that was the kind of peripheral interaction I had with Professor Mitra. But as the earlier speakers, many of them were his former students, have pointed out, he's one of the stalwarts of Indian physics. And it's great to remember him on this day. So in my talk, I'm not going to speak about the kind of topics, particularly particle physics topics, which have been dealt with by many of the earlier speakers, but I will deviate quite a bit from that. I will talk on some recent developments associated with nonlinear dynamics and some connection with artificial intelligence, artificial neural network, and so on. So there has been recent attempts to connect nonlinear dynamical systems with these kinds of developments. As we know that artificial intelligence is one of the important topics that is being considered, whether it's part of physics or part of engineering or whatever it is. But with the award of 2024 Nobel Prize to Professor John Hopfield and Geoffrey Hinton, this connection has become more and more intense. So in my today's talk, I will give a brief overview of the notion of reservoir computing, and then using just a simple nonlinear map, the so-called logistic map, as the reservoir, I will try to demonstrate how non-temporal and temporal tasks, I will explain what it is, non-temporal and temporal tasks can be accurately predicted. So this will be the plan of my talk after a brief introduction about artificial intelligence and artificial neural network and so on. I will introduce logistic map, a very simple nonlinear dynamical system, and use it as a reservoir. And then I will point out how, for example, polynomial functions can be predicted with the prior knowledge of few data. Prediction of non-temporal tasks, any order of polynomials, for example. And then temporal tasks, for example, the dynamics of nonlinear oscillators. So I will try to point out how non-temporal and temporal tasks can be predicted with this point out. As you know, artificial intelligence, which corresponds to any technique that enable machines to solve a task like humans do, and in which machine learning is a subtopic, algorithms that allow computers to learn from things without being explicitly programmed. And artificial neural network is brain-inspired machine learning models, and out of which a smaller subtopic is deep learning, and so on and so forth. So considering neural networks, for example, the human brain is a very complex dynamical systems, billions of basic entities called neurons with very complex connection. The collective dynamical behavior is how our brain acts. The single dynamical unit is the single neuron, which has three major elements, namely the central nucleus, out of which tree-like dendrites emerge, which collects information from other neurons and then pass information in the form of electrical signals along cylindrical kind of tubes, namely axons. So this is the standard neurons in a brain. But artificial neuron, which resembles in some certain sense human brain, consists of certain number of inputs, x0, x1, x2, xn, connected through certain weight functions in a linear way, then a linear function z, involving all these inputs. And then this is connected to an activation function, which could be quite nonlinear, to give rise to the desired output. So that is called a perceptron, a basic unit of an artificial neural network. And then this artificial neural network, you have deep neural network and recurrent neural network and so on. So a perceptron is one of the simplest types of artificial neural networks. It's a computational model that mimics the behavior of a biological neuron in the human brain. On the other hand, so for example, in the perceptron, you have a large number of inputs are connected to a single node, and then from which, through the action of this activation function, you get the output. Whereas in the case of deep neural network, so you have a large number of input layers, and that is collected to multiple number of nodes. Each one is connected to all other nodes, and there are several nodes, multiple hidden layer it consists of, and from which output layer is connected. So this is a more general version of ANN. And then you have also a recurrent neural network. The standard neural networks cannot handle sequential data, but considers only the current input. So it cannot have memories. But whereas the solution to these issues is the recurrent neural network. So you have the neural network, the hidden networks, which are unfolded, and you have a large number of hidden networks. So you have several inputs, and they are connected to these hidden networks, unfolded networks, and then you extract the outputs. The solution to this is the RNN, and RNN can handle sequential data, accepting the current input data and previously received inputs. So RNNs can memorize previous inputs due to their internal memory. And out of which this reservoir computing, which is an RNN-based framework, which is quite efficient in training to perform a given task. Highly efficient and practical approach for various machine learning tasks. Computational effort is considerably reduced here. And in particular, we have found recently the reservoir need not be a very large complex network. And it can be any kind of nonlinear dynamical system. And very surprisingly, we find it can be as simple as the logistic map, which is very basic unit studied in a nonlinear dynamical system. So the logistic map is you have a dynamical entity omega at the present instant, discrete instance n, at the nth instance omega n, and that is connected to the next instant omega n plus 1 through a parameter a. Omega n plus 1 is a equal to a into omega n to some nonlinear function minus a omega n square. That is a omega n into 1 minus omega n. So for some i's, okay. So omega n plus 1 is a omega n into 1 minus omega n. So this is the basic nonlinear dynamical system, the logistic map. And it has very beautiful dynamical structures. For example, you have the so-called bifurcation and chaos coming in this simple dynamical system. So you have the dynamical system omega n plus 1 equal to a into omega 1 minus omega n. And one can show that omega can be confined between 0 and 1, while the parameter a can be confined between 0 and 4. That is sufficient to consider the dynamical system. And you find as you vary this control parameter a from 0 to 4, you find very interesting dynamical features. So first, you have the period 1 behavior, period 1 dynamical state, which at a critical value a equal to 3, it bifurcates, it loses stability, and in place of that, a period 2 state emerges, which goes on up to 3.6 or something like that. Then it again bifurcates. So period 2, then period 2 power 2, that is period 4, period 8, period 16, 64, which all occurs in a very narrow range, following a particular universal constant called Feigenbaum ratio. And then at a very critical value, 3.656, etc., it enters into a very complex state, namely chaotic state. You can have infinite number of possible solutions at that point of time. So this is the basic structure of a nonlinear map, namely the logistic map. So I will try to use this map as the reservoir so that these various states, omegas, will form virtual nodes. So you have for a given system, the inputs U1, U2, a finite number of inputs, U1, U2, U1 up to L number of finite inputs. I map this L number of inputs on this parameter A. So I call that as AI in a linear, through a linear transformation. And because of that, I have several possible states for every UI. I have AI, I have mapped linearly to AI. And for that AI, I iterate starting from n equal to 0, omega 0 at a particular value. For example, I choose omega naught as 0.95. And then I iterate, I get omega 1, omega 2, omega 3 for this UI, for this ith value. So I get P such possible values or L such possible states, P such possible states. And for every use, then I get such possible states. I collect all of them, and that forms the reservoir state matrix. And from that reservoir, so that contains information multiplexed, input information multiplexed, extended, and I connect that to the output through a linear transformation. And that linear transformation is through a weight matrix W. I associate that weight matrix. In this way, I can connect, I can identify a reservoir through a very simple nonlinear dynamical system and obtain the outputs. So in this method, the reservoir is constructed by the virtual nodes using the logistic map as the reservoir computer and encode the inputs as temporal patterns. And we can prove the universality of this method both for non-temporal tasks, for example, fitting of a trajectory or a curve with a sampled few data points, or predicting temporal tasks, predicting nonlinear chaotic systems, for example, a Lorentz system or a Rössler system or a Hindmarsh or any other nonlinear dynamical system. So I will first demonstrate how you can identify, predict a polynomial function, for example. So consider a finite number of samples for a given polynomial functions between two regions, between two endpoints. So let between two limits, u minimum and u maximum. Here, u minimum and u maximum are the minimum and maximum of the function of x of a function f. So x is the independent variable and f is the dependent variable. So you want to find a function f of x. Given x, the range of x is limited between x equal to u minimum, minimum value minus 3, for example, and maximum value plus 3. So a finite number of points are given. And then you want to predict the function in the entire range between minus 3 and plus 3. So one way of identifying this function is that the given inputs x1, x2, x3, L inputs xi is ui and the outcome f of xi is vi. So that is the given input. Ui and vi are known values of input and output respectively. Now, with each of these ui, I supply this to the logistic map equation through a linear transformation. Ui is given, and I have u maximum and u minimum, I have fixed. So I try to associate with A through this linear transformation. So I find a quantity, a parameter ai through A minimum, A maximum, similarly I fix. Then through this linear transformation, ai constant into ui minus u minimum. So I can find an ai, and for that ai, I iterate omega. So start from n equal to 0 for a minimum and a maximum corresponding to this logistic map, either in the periodic regular regime or in the chaotic regime. Okay, between an a minimum and an a maximum. And then if I do that, so for each of this given ui, I can get p number of omegas by iteration. Okay, for every value ui, I get p omegas. So ui is mapped down to ai, which in terms of the omega map, the logistic map, gives p number of data. So the data is multiplexed. The input data ui is multiplexed via the parameter ai, and then through the logistic map into p data points. So I can construct a reservoir state vector corresponding to this input ui as omega 1i, omega 2i, etc., omega pi. Okay. This I carry out for all these L inputs, U1, U2, UL. So for each of these inputs, U1, for example, I get an P into 1 column matrix state vector. For U2, I get again a P into 1 column vector, and so on. So that for this entire set of given input data, I get a P by L reservoir state vector matrix. Okay, so that is from the knowledge of input information, I construct a state vector matrix of the reservoir. Once I get the state vector matrix, so what I have done was, given the input U1, U2, etc., UL of that polynomial function, through this parameter, through this linear transformation and the logistic map, I construct the state vector matrix, okay, which is of the form P, the order P by L matrix. R is the reservoir matrix. So the 1 by L size input vector is mapped down to a higher dimension size P by L as the reservoir state vector matrix. Now, from the reservoir state matrix, I construct a weight matrix because the given input information is input L input information and L output information that is given. So since I know the outputs, I relate the input with the output through a linear transformation. the input has been multiplexed through the state vector matrix R, and I assume that the output is related to the input through a linear transformation, and that gives the weight matrix of the order 1 by P. So I can always construct, because I know information about from input, the reservoir matrix, and the output I know, so I can construct W as V into R inverse. V is the given output, and R is the reservoir matrix, which I construct from the inputs. So R will in general be a non-square matrix, and through Moore-Penrose pseudo-inverse theorem, it does exist. I can identify that. With that information, now I try to construct the entire function f of x between the minimum value u minimum and u maximum for any other inputs, any other input values, which I call as u1 prime, u2 prime, u3 prime, ul prime. And L prime need not be equal to the previous cell. It can be any number through the same input, the weight matrix. So with these new inputs, I try to construct a new state vector matrix R prime, as I pointed out earlier. So I construct this state vector matrix, and then I have already information about the weight matrix. So the unknown output function can be constructed through the capital V equal to W R prime, where capital V is the corresponding output vectors which are obtained through this linear relation. So I can get the output function. And to check the accuracy of my prediction, I use the statistical measures, error measures, the root mean square error, square root of Vi minus Vi square, where Vi is the actual output value set for the corresponding predicted output is Vi. So I calculate the root mean square and the normalized root mean square RMSE by sum over Vi minus V average by L prime. So in general, for a prediction to be good, this normalized root mean square error should be much less than 1. So that is the criteria I will use. So for example, I will construct a 7th degree polynomial. So suppose you are given a 7th degree polynomial x minus 3, x minus 2, etc., x plus 3. It could be symmetrical or non-symmetrical. Then I apply the procedure I have given above. For example, 20 input data sample is given, and the corresponding output is given. So I construct the state vector matrix. Then for any other value in between this minimum minus 3 and maximum plus 3, I can take, for example, 100 unknown points, input points, and construct the corresponding output function. Then I plot the unknown functions, and you see that you get exactly the correct form of the function, this polynomial function, in exact way. So here the dots correspond to sample data, and the green curve corresponds to the target, and the red dots, which are followed on the green dots, which you cannot really distinguish, but they exactly follow the target correctly. So the 7th degree polynomial can be constructed with A minimum, A in the periodic regime, A minimum equal to 0.1, A maximum equal to 2.2. I have restricted. Within that, I have iterated 20 times, and the inputs are 20 inputs, but the unknown outputs, inputs are 100. So with that, I can design the polynomial function exactly. And I can also do this in the chaotic, again, periodic region, but by introducing certain errors in the small error, noise, for example, 0.1, uniform noise, 0.1. Even in that case also, the function can be exactly predicted. And similarly, I can carry out this analysis for the chaotic region of the logistic map. Again, I can construct exactly, and the normalized root mean square error is, again, very small, of the order of 10 power minus 5, and so on. And then for a 9th degree polynomial, for example, again, I can construct the function exactly. So thus, this prediction is done in a narrow region of the logistic map of the order of 0.1. But suppose you have a large number of input data that is given, which is outside this region. You can extend this region by following further modified procedure. For example, you multiplex by introducing a trigonometric function and extending this and introducing a continuous function. And again, you can generalize the procedure I have given, and you can identify the function exactly accurately. So prediction of such non-temporal tasks through this logistic map can be exactly carried out. I can extend this study for temporal task. For example, next I can perform the temporal task of predicting the time series of one variable of a nonlinear system by supplying the time series of another variable of the same system. For example, for the Lorentz oscillator or Osler oscillator, Hinmar's oscillator, etc., I can predict the variable in an exactly similar fashion. And for this purpose,
sorry, Professor Lakshmanan, I apologize for interrupting you. Please excuse my impertinence. Just wanted to remind ourselves that we have about 3 odd minutes left for your talk.
Yeah.
So if we could wind things a bit so that we could possibly incorporate some QA for your talk.
Yeah, I will finish the next 1 minute. So I can generalize this by providing information about the past in a sequential way, and I can follow as before. I can predict so like weather forecasting or stock marketing and so on. I can also dynamical system. I can give input information for a certain number of previous times, so m number of previous times, and then I can again construct a state vector for each of the inputs, and then generalize that and construct the state vector matrix, which will be of larger dimension. And for this continuous system also, again, I can construct a weight matrix, and from which I can obtain the time series, for example. I can, for example, if the Lorentz system is a system of 3 coupled nonlinear ordinary differential equation, and given the input information for x, y, z for finite number of times, so that the training is done for a finite number of times, and then I can predict the variables for the remaining times very accurately. So the green curve corresponds to the target trajectory, and the red dots correspond to prediction. And you see the red and green dots follow exactly each other. And so the prediction, again with the logistic map, can be exactly carried out for all these Rosler system, Hinmark systems, or even higher dimensional systems very accurately. And so you have three-dimensional dynamical system, and given input for one information, then I can construct another variable. But I can also construct the same variable, that is self-prediction, that can also be carried out exactly, very accurately. And I will conclude my talk with this following reference: the recent work of my group, Arun, Satish, Venkatesh, myself in Physical Review, Reservoir Computing with the Logistic Map, and Machine Learning Potential of a Single Pendulum by Sinha Srimali in Physical Review, and so on. And you can get the details of the logistic map, for example, in my book, Lakshmanan Rajshekhar, Nonlinear Dynamics, Integrability in Chaos. So thank you very much, and I will be happy to discuss further. Any questions, comments, welcome. Thank you very much.
Thank you, Professor Lakshmanan. Thank you so much. So maybe you could have one quick question. I see Professor Kaushal. Please go ahead.
Professor Lakshmanan, yes. This your weight matrix is in some sense is a translation of coupling between artificial intelligence and natural intelligence. Is that kind of, can we say like that?
No, the weight matrix connects the reservoir, which consists of data about the input. The input has been multiplexed and converted into the reservoir. And so that contains information about the input and how
It's a
it's
kind
to the
you
output.
see,
So I connect it through a linear transformation, and that is the weight matrix. Yeah.
there's a coupling between artificial and natural one. So that kind of thing, how will you account? Through that reservoir or weight matrix we have generated?
Yeah, the reservoir is can be related to the artificial neural network.
Mhm.
Yes. Okay.
So I think with that, let us thank Professor Lakshmanan. Thank you so much.
Thank you.
And,
Thank you.